Okay, welcome to week 4, part 2. We've been flogging away at pandas for the last couple of lectures, talking about how to organize and wrangle data. So we're going to take a look now at, we're going to return to the business of statistics a bit. We have previously described 4 different variable types. Nominal or categorical data that you can tell apart from each other, and we looked at pizza toppings as one possible example. They're either present or not present on a given pizza, and there is only sort of minor wow, there is only sort of minor statistical stuff that we can do with these kinds of data. We can count frequencies and percentages and figuring out which ones are the most common and so on. Ordinal data is ordered, but not in a measurable, continuous way. The example that we talked about was gold, silver, and bronze medals at the Olympics. Those are clearly ordered. Gold is best, silver is next best, bronze is third best, but there's no notion of distance between those. And we also have a similar kind of limited sort of statistics that we can do with those, although we can talk about ranges, we can talk about medians, we can talk about rankings. And then intervals are data that do have discrete intervals that are in some sense the same width or the same value. And for information like this, we can get into being able to compute means, variances, standard deviations, do t-tests for significance of various hypotheses, compute correlations between different types of, different sequences of values. And then finally we have ratio, where we do have a very definite continuous ordering of values, like for people's ages, and we can do the most statistical analyses with these. All right, well, so basically what we've been working with so far has been what's called descriptive statistic on observed data. We've just concerned ourselves with describing the set of data that we have, computing means, medians, modes, standard deviations of numerical kind of data. But we haven't made any effort to relate the data that we have back to the world as a whole, all right? And this is something that we're going to get into talking about now, is a bit about what's called inferential statistics. We've only been doing descriptive statistics so far. Okay, so basically, probability and statistics are often talked about as a thing, studying probability and statistics. But in fact, those two are sort of mirror images or inverses of each other. In probability theory, we have some kind of world, some kind of process that is producing results, and we know how that world works. For example, we know very definitely how six-sided dice work. We know very definitely how standard decks of 52 cards work. We know very definitely, at least from a statistical point of view, the decay rate of various radioactive elements, things of that kind. And so given the knowledge that we have of this process that's generating these observations, we can simply compute probabilities of observing different collections or sets or organizations of results. Like we can predict very exactly what the probability is of rolling a 12 on 2 fair dice, and we can predict very accurately what the probability is of drawing a face card from a standard deck of playing cards and things of that sort. Now, statistics is concerned. First of all, we've talked about descriptive statistics, which has to do with just describing a particular sample of observations that we have. But more generally, statistics is concerned with making inferences about the world or about the underlying data generating process based on an observation, a set of sample data that we have. All right. So if we know exactly how the process works, then we can compute probabilities of observing certain kinds of things. But on the other hand, if all we have is observations of certain kinds of things, and we're not sure how the process works that generates that, then based on the data that we have and based on statistical analyses that we can perform, we can draw some inferences and make some predictions about how that, how the underlying world is working. Okay. All right. So we have a population. I have been doing demos and playing around with certain kinds of statistics involving a sample of dogs that are legally registered in Allegheny County during the year of 2024. That was the sample that I found, and we computed the the number of the different breeds of dogs, the frequency and popularity of various different breeds, the frequency and popularity of various different dog names, the categorized by breed. We figured out what average weights for adult dogs were. We took a look at the age ranges of dogs of different breeds, all this kind of stuff. Just describing dogs legally registered in Allegheny County. Now, there are millions of dogs. So our population of dogs is larger than we can possibly measure. But we would like to be able to make use of the sample of dogs that we have from Allegheny County to make some inferences about what's probably going on in the population of dogs as a whole. All right, so that's what's called inferential statistics. All of this is built on top of an understanding of the underlying probability and various kinds of distributions that can occur. Here we have a diagram illustrating one kind of probability density function. This is a continuous probability density function. And so if we pick a particular value A, the value of the f of A at this point is not a probability, but if we measured a narrow window around A, we would be able to figure out some kind of probability of being within a certain interval around A. Okay, basically the area of the curve in the vicinity of A is the probability of falling within that particular range. Okay. That's a little hard to contemplate, especially when you're looking at a curved density function. So an alternative that makes things a little easier to visualize is something called the cumulative distribution function, which is simply it is a curve representing the area under the curve, the cumulative probability of observing values less than or equal to some value A. All right. So instead of areas, as we do in the probability density function, we can convert that to just looking at levels in the case of the cumulative distribution function. And so necessarily the cumulative distribution function starts with a value of 0 because there is 0 probability of observing a result prior to where the distribution starts. And necessarily the cumulative distribution function has to climb or become asymptotic to 1. For example, let's suppose that this distribution represents the probability of being a certain distance from the bullseye if you shoot at a target. All right, so the probability of being, the probability of being pretty far away from the bullseye on the target is probably pretty low in the negative direction. It's also pretty low in the positive direction. Here we're assuming we're just talking about distances to the left and right. The probability of being close to the bullseye is higher because we're aiming for the bullseye. So we'll get a distribution sort of like that if we're just looking at the distance from the bullseye to the left and right. And if we look at the cumulative distribution function, then we would say the probability of shooting a bullet is 1. Okay? If we shoot a bullet, it's going to land somewhere, and so the probability that we shot a bullet is going to be 1. On the other hand, if we haven't shot a bullet, then the probability that we're going to hit anywhere near the bullseye is going to be 0. I'm not sure that was a wonderful analogy. Anyway, here we go. The so-called normal distribution is vitally important in statistics for a number of reasons. First of all, a great many natural processes do follow a normal distribution or some adjusted form of the normal distribution, such as something called the log normal distribution. That applies to a lot of financial-related returns. And you've probably got various percentages memorized here. This diagram is not completely wonderful, but within minus to plus a standard deviation of the mean, we have approximately 2/3 of the values in a normal distribution. It's 68, very close to 68%. And then within 2 standard deviations of the mean, we have 95% of all the observations. And within 3%, within 3 standard deviations, we have about 99% of the observations. Now, it is possible to have, observations that are further away than 3 standard deviations from the mean, but those kinds of observations are quite rare. So the normal distribution is very beneficial itself as far as describing a lot of natural processes in the world. It's also very important because of the central limit theorem, which we fervently hope you remember. All right. Basically, the idea here is that if you have many values taken from independent and identically distributed random variables, then the sum of all of these, if you take samples of a certain size over and over again, the sums of those samples will converge to a standard normal distribution. And it turns out that it doesn't even matter what the underlying actual distribution of the individual observations is. Here's a bit longer statement. So if we select a random sample of n observations from any population, okay? And if the population has a mean value of mu and a standard deviation value of sigma, then no matter what the distribution of these observations is, as your sample size gets larger and larger, the distribution of the means, oh, that's interesting. All right, it won't let me highlight X bar. Trying to highlight X bar here. The distribution of these means of samples of size n approaches a normal distribution itself. And the relationship of the mean of the sample and the standard deviation of the sample is as follows. The mean of the sample gets closer and closer to the actual mean of the underlying population as your sample size gets larger. And the distribution, the standard deviation of the sample size is related to the underlying standard deviation of the population according to this formula. The standard deviation of the sample means becomes or approaches the standard deviation of the population divided by the square root of your sample size. Okay, so the bigger your sample size gets, the smaller the standard deviation around the sample mean gets, and therefore as the standard deviation of your sample mean reduces because your sample size is increasing, the mean of the sample gets closer and closer and closer to the true mean. All right. So that's an amazing result because it means that we can get very close to the actual mean of the observations that were, of the observations that we're getting of this population, just by controlling for the size of the sample that we take. All right, so one whole point of any distribution is we want to identify the so-called central tendency. That is, we want to answer the question, what is a typical value that we're likely to observe? And what other characterizations can we make about this data, like what is the actual standard deviation for the population as a whole. Now, what is a typical value varies. We know that we've got at least 3 different ways of describing a typical value. The mode is the value that is most often seen. The median is the value which half of the values that we observe are less than that and half are greater. And then the mean is simply the sum of all the observations divided by the number of observations. And each of these has its good points and its bad points. One of the issues involved in selecting these different measures of central tendency has to do with the skewness of the actual underlying distribution. If we have a heavily left-skewed distribution, like here we've got distributions of weights of something, and here this is just a histogram counting the number of occurrences of these weights. Maybe these are, I don't know, weights of young kids, where a lot of them are in the 40 to 50 pound range, and then we have a few going all the way up to 140 pounds, whatever. The mean here is going to be to the right of the median. The median value, where half of the, imagine these are kids being weighed, half of the kids are below the median and half of them are above the median. The median is going to be sort of skewed to the left toward these taller frequency counts. And the mean is going to be to the right of the median because these larger values will have what am I trying to say? A greater impact on the mean and relatively little impact on the median. And then the mode here would simply be the tallest, the weight with the tallest bar, and that may or may not tell us something of value. So you don't learn much from only knowing the mean or the median or the mode. Those are kind of minimum necessary pieces of information for describing a distribution, but you also need to know more information to understand how the distribution actually looks. You need to know about the standard deviation. You need to know about the skewness, etc. All right, so here we have an image of a plain ordinary normal distribution. I don't know how plain ordinary that is. And here are the formula for the probability density function. The mean and the variance are what are called the sufficient statistics for a normal distribution, because it turns out that the normal distribution is so cleanly and symmetrically defined that all you really need to know about it is its mean and its variance, and all of the other characteristics of the distribution just fall out of those 2 particular values. Here are some non-normal distributions. Well, this bottom one is normal, but here are a couple of non-normal distributions. Here we have a triangle distribution with, I'm not sure what distribution, what process this is representing, but this is the density function for this triangle, and here we have the density function for this uniform distribution. And over here to the right, we have the cumulative distribution functions, again, starting from 0 and climbing up asymptotically to 1. Notice that the uniform distribution here is from the interval 2 up through 6. That necessarily means that the areas between 2 and 3, 3 and 4, 4 and 5, and 5 and 6, that those areas are each 1/4 of the overall area, and that's why we've shown the height here as 0.25. Okay, because if we add up 0.25 1, 2, 3, 4 times, that gets us to a probability of 1, and so the cumulative distribution function just climbs linearly from the left edge up to the right edge. Here's another image of a. This might be a histogram of observations drawn from a normal distribution. This particular normal distribution, uniform distribution. So this particular uniform distribution is on the interval from 0 to 1. And for the purpose of the histogram here, it looks like we have binned things into 0.05 width bins. All right, so we've got 4 bins until we get up to 0.2. And this is showing us the frequency of the of draws from this particular uniform distribution. The more draws that we get, the closer and closer and closer this thing is likely to converge to looking like a true rectangular uniform distribution. But there are obviously going to be some bars that are below the mean and some bars that are above the mean. Here we have another distribution called the exponential distribution that demonstrates an exponential decay. We've got the formula for the density function and for the cumulative density function. We also have the formulas for the mean and the variance for the uniform and for the exponential. You can, investigate other kinds of probability distributions to find out about their formulas and means and variances as well. Here's the binomial distribution. Now the binomial distribution, it turns out, converges to a normal distribution as the number of samples that you draw increases, which makes sense given the given the central limit theorem's statement about the means of samples of size n converging to the mean of the overall population. All right. Now, conceptually, we're aware that a distribution with a small standard deviation is going to have a tighter density function than a distribution with a wider standard deviation. And so if our primary concern in looking at a distribution is to, as accurately as possible, identify the mean value, then it makes sense for us to draw a larger and larger and larger sample size to try to narrow down that the standard deviation around the mean of the samples. Now, to compare variables to each other, a certain issue arises. What if the scales of the variables that you're trying to compare to each other are not directly comparable. For example, when the admissions folks evaluate people to be admitted to our master's programs, one of the variables that's involved is GRE scores, which can range from 130 to 170 for the verbal part and for the quantitative part. So we've got a total of ranging somewhere from 260 to 340. And we also have language exam, I believe, is the TOEFL exam. I have not had to take that myself. Yes, that's embarrassing. I had to pause for a moment to look that up. But yes, test of English as a foreign language, 0 to 30 per section with a maximum score of 120. I don't know why this keeps skipping forward. And a third thing that we look at is GPA, which might range from 0 to 4 or 0 to 5 or whatever, depending on the educational system that you were part of. So how can we figure out how to compare or add together, if you will, these GRE and TOEFL and GPA kinds of scores? Well, what we can do, and these are ratio variables, what we can do with a ratio variable is to either standardize or normalize the score. So let's take a look at what we mean by those two different terms. Normalizing means, good heavens, normalizing means to update all of the values so that they fall within a range from 0 to 1. And we do that by identifying the maximum value and the minimum value. That is, the maximum minus the minimum is our divisor. And then we have the particular x value of an observation. We subtract the minimum from that and divide by x max minus x min. Now, obviously, you can see that if the particular observation that we're looking at is equal to the max, then this value that we'll compute is 1. And on the other hand, if this particular observation for x that we're looking at is equal to the min, the result will be 0. So if all of our observations fall in the range from x max to x min, which by definition they have to, because x is simply the maximum of the observations we have, and x min is the minimum of the observations we have, then this formula clearly scales every single observation to fall in the interval between 0 and 1. Okay, and so that's what we call normalizing. Normalizing. Now, this is nastily affected by outliers. If our x max is, let's say 10 times larger than the next available, than the next higher observations, that may mess up the normalization. We're going to have a whole lot of values that are pretty close to 0 and only one value that's at 1. What do we do about this? Well, I don't know. Do we evaluate that outlier and decide whether that outlier is legitimate? Or do we decide that that outlier is an error and get rid of the outlier? This is the whole quandary of cleaning your data before you start getting into the actual statistical analysis that you want to perform. For some areas of study, outliers are dangerous and ought to be tossed out. And it depends very much on the knowledge of the analyst when this is the case. If I were doing analysis of daily temperatures in the Badlands of South Dakota, and I had a daily temperature in my sample that was 250 degrees Fahrenheit, well, I know that that's physically not possible. That's way above the boiling temperature of water. I know it can't possibly have gotten that hot on some day in the South Dakota Badlands, despite that they're pretty hot during the summer. On the other hand, if I am dealing with financial data and I am looking at the daily returns on stock prices, and I'm looking at a particular stock, and I discover that most of the time the daily return is, down pretty close to zero. Sometimes it goes down a little bit, sometimes it goes up a little bit. And here I've got this one day that's got a 35% increase, and another day that has a 10% decrease. Do I just assume that these are bogus outliers and throw them away? Heavens no. Heavens no. Financial data does tend to have outliers like this, and it's those outliers that determine when most of the money is made or lost. You can have a stock that does nothing for a year and a half and then suddenly has some really good news and shoots up 20 or 30% in a day. That doesn't mean that's an outlier and that you should ignore it. So this outlier detection stuff in general is a very difficult problem for which there's not a trivial solution. Okay, so that is the idea of normalizing. Bringing all the different variables, values, into a range between 0 and 1. Standardizing, on the other hand, has to do with taking your observation and subtracting from that the mean of all the observations and dividing by the standard deviation of your observations. The idea here is to get a difference, a scaled difference, scaled by the standard deviation of the value either above the mean or below the mean. This relates to what are called z-scores. The z-score for an observation is that observation minus the mean of all the observations divided by the standard deviation of all the observations. And the idea here is to scale the value to fit reasonably into the form of a normal distribution, so that we can think in terms of how many standard deviations above or below the mean is this particular value. All right, so whether we standardize or normalize these various scores, we end up with all of them having similar scales, so that we can simply add them together, or we could compute a weighted mean of these standardized values, or these normalized values. Perhaps we consider the GRE score to be to have 2 or 3 times the weight of the TOEFL score or of the GPA score. So we can, once we have standardized and normalized these scores, we now have everything on the same scale so that we can meaningfully compute, statistics based on these scores. Okay. Well, how else can we compare variables to each other than this idea of normalizing or standardizing the variables? Well, we can compute the covariance or the correlation between, I should say the covariance and the correlation between our different variables. Here we're assuming that the two variables that we're comparing arrive as pairs of information. If I simply had a huge bag of temperature readings for a certain location in South Dakota, I seem to be fixated on South Dakota today, and I had a huge bag of humidity ratings for some location in South Dakota. If I didn't know when these readings were taken, I would not be able to deduce anything about whether temperature and humidity is correlated. So I would have to have, at specific time points, in this case, I would have to have a temperature reading and a humidity reading that occurred at the same time. And ideally, I would like to have those temperature and humidity readings be at definite time steps, so that I could even do some time series analysis on those values. But let's suppose we don't have the time steps. We just know that each of these pairs of values that we have, temperature and humidity, occurred at the same time as each other. Well, then we're in a position to compute the covariance or the correlation and the correlation of these two paired variables. We may discover that as temperature increases, humidity increases or decreases. We may discover that as temperature increases, there's no noticeable impact on the humidity one way or the other. Covariance is, for me at least, a little bit difficult to think about in intuitive terms. Correlation is I hesitate to say normalized. I guess it is normalized. Well, of course it's normalized. Correlation is a normalized measure of the covariance, except that instead of having values between 0 and 1, we have values between -1 and +1 for correlation. Okay. Now, so let's suppose that this is a diagram of temperature on the horizontal axis and humidity on the vertical axis. If those points of data that we have all lie on a perfect line that has, in this case, a negative slope, this gives us a correlation of -1. That means that when the temperature goes up, the humidity definitely goes down by some linear kind of relationship. Notice that correlation is not the same as slope. This is a negatively sloped line. It doesn't appear to have a slope of -1. It looks more like it's got a slope of minus 0.5 or something like that. But correlation is not telling us the slope. It's telling us how on the line those particular values are. Now, in this next diagram, to the right of the perfect negative correlation, here we have a negative correlation, but it's not a perfect correlation. We see that there's a tendency as temperature rises for humidity to fall, but the values are off of that perhaps least squares line that's been drawn through the data. Sometimes when the temperature goes up, the humidity goes down. Sometimes when the temperature goes up, the humidity goes up. On average, it seems that as the temperature goes up, the humidity goes down. But it's not a perfect correlation. So it is a negative correlation, but it's not perfect. And over here, the very last one, here there is no correlation at all. There is no evident linear relationship at all between what happens when temperature goes up versus what happens with humidity. It seems to the humidity seems to be just all over the place, regardless of where the temperature happens to be. All right, so these two graphs on the top are negative correlations. That is, when our horizontal variable is increasing, the vertical variable is definitely decreasing by by the same amount, not as the horizontal increase, but it's decreasing at a specific rate. Okay, so as the horizontal value goes up, the vertical value is decreasing at a specific linear rate. Here we have positive correlation. When the temperature goes up, the humidity tends to go up. It's not a perfect linear relationship, but it is a tendency to go up. And here in the fourth of these diagrams, when the temperature goes up, the humidity goes up in a very linear way. Okay, when the temperature rises, let's say from 50 degrees to 55 degrees, we see a certain rise in humidity. If the humidity rises from 80 degrees to 85 degrees, we see the same proportional rise in humidity over that 5-degree difference. Okay, so this again is perfect positive correlation. Not the same thing as slope. This slope looks pretty shallow. It looks like it's, maybe like 0.3 or something like that. Now, there's an image that's not shown here that's worth thinking about, and that's a perfectly horizontal line or a perfectly vertical line. Now, if the line is perfectly horizontal, of course, the slope of that line would be 0. But the correlation is also 0, because as we increase our temperature, we see no change going on in the humidity. So there's no correlation. That is, we observe temperatures, but the humidity never changes depending on the temperature. So there's no correlation in that case between the temperature and the humidity. Similarly, if the line were vertical, so that as the humidity increased, so that increasing humidity had no was not any kind of consequence of temperature. That would also be a correlation of 0, even though the slope is undefined, infinite, or whatever undefined. Okay, so that's the idea of correlation. Now, okay, and these slides say more of what I was just basically describing. Covariance is an indicator of how two random variables are dependent on each other. Higher numbers denotes higher dependency. Higher magnitude numbers denote higher dependency. Of course, the covariance can be positive or negative. But the normalized version of that, the correlation, is a lot easier to directly comprehend. Now, it turns out that correlation is simply a normalized computation on the covariance. We compute the covariance and we divide this covariance by the standard deviation of the two, actually, to get the the correlation. You can look up in infinitely many sources the exact computations for the covariance and the corresponding correlation. Now, in terms of values, the covariance can take on any value at all, from negative infinity to positive infinity. The correlation always has to fall between -1 and +1. That is perfect negative correlation or perfect positive correlation. If the variables are moved around in terms of scaling or offsets, then the covariance will be affected. One of the cool things about the correlation, though, is that it's not affected by any changes to the variables. Here is specifically what that means in terms of mathematics. If I am computing the correlation between two random variables, x and y, that correlation is going to be the same as a correlation that I compute having scaled x and offset x by some amount, and also having scaled y and offset y by some amount. So linear transformations on these random variables will not have any impact on the value of the correlation that you compute between the original variables or the scaled and offset variables, whereas the covariance will change. So that's yet another reason why the correlation is easier to deal with than the covariance. Well, so what can we deduce from looking at the covariance and the correlation between some variables? Here we've got a sample with 146 elements. The mean value of our x values is 53.7. The standard deviation is 15.78. The mean of the y values is 49.1. And the standard deviation of the y's is 24. Fine. That tells us what the mean of the x and the standard deviation of the x is, and what the mean of the y and the standard deviation of the y is. So that gives us some information. But this quite low correlation value is more meaningful as far as how these variables relate to each other. There is a slight negative correlation, but the correlation is pretty close to 0. And thank goodness that that's true, because the data that this is computed from is a digitized outline of Barney, the purple dragon, I believe. Okay, so thank goodness there's no apparent, there's very little apparent correlation among these values. It does look like if we, drew a least square line through here, it would have some kind of negative slope, but not very much in the way of correlation. Now, what if we do have high correlation between two different variables? Does high correlation between variables imply a causal relationship between those variables? And so here we have this cartoon. I used to think that correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe. All right, so as an illustration, we've been given 6 months of information about a city. And we have all kinds of variables, and we observe that on days when there is an increase in the number of bicycle accidents, there is also an increase in ice cream sales. All right, so we observe a strong positive correlation between these things. When one is going up, the other is going up. So does that mean that ice cream is a cause of bicycle accidents? Well, clearly, that's absurd. It's absurd that that would be the case. What's much more likely, and in fact makes sense, is that each of these observed variables share a similar cause. Now, bicycle accidents, we can imagine, depend mostly on how many bicycles there are out on the road. If we have twice as many bicycles, maybe we would have twice as many accidents, and so forth. Likewise, ice cream is going to depend on, how many people are out wanting to buy ice cream. So perhaps the issue here is that on pleasant, sunny, warm days, a lot of people are riding bicycles and a lot of people are eating ice cream. And because a lot of people are riding bicycles, we see an increase in the number of bicycle accidents, while at the same time we're seeing an increase in the amount of ice cream that people are eating. Okay. And so, and so that's the same conclusion that's drawn here. Okay. Here's another actual observation. This is non-commercial space launches each year, and the American Sociology doctorates awarded each year. And golly gee, those look pretty correlated. But there can't possibly be any causality between space launches and sociology doctorates. So this is an example of what's called a spurious correlation. And it's something that you need to watch out for carefully. Likewise, here we have the high school graduations in blue and donut consumption in red. Again, these look really correlated, so maybe you should eat lots of donuts if you want to graduate from high school. Well, no, this is just population growth. As the population grows, decade after decade after decade, if donut consumption remains fairly constant for the population and the rate of high school graduation remains fairly constant for the population, these are going to be highly correlated, even though one does not cause the other. They are both caused by the same thing. And more similar examples. Comic book sales versus computer science doctorate degrees awarded. Injuries related to falling televisions versus undergraduate enrollment at universities. Now, both of these, again, are simply functions of increasing populations. As the population goes up, the number of comic books sold is going to go up, and likewise, the number of computer science doctor's degrees is going to go up, and the number of injuries related to falling televisions and undergraduate enrollment at universities, all of these things are going to go up. And the fact that some of them look sort of startlingly like others is pure coincidence. And here we have, this one's not quite as perfect, but tornadoes annually versus shark attacks annually. Clearly there can't be any causal relationship there. Okay, so hope that is of some benefit. Remember to think about normalizing or standardizing information so that you can compare different types of information to each other in a meaningful way. Think in terms of figuring out the correlations between different variables to see whether they are uncorrelated or highly positively or negatively correlated, and beware that correlation does not imply causation. I guess as a final thought there are actually people in the world who believe that the rate of increase of sunspots or decrease of sunspots has some kind of effect on financial markets. So, so watch out. All right, take care.